present speaker of today, of colloquium of today. So it's Professor Vadim Geshkenbein from the Technical University ETH in Zurich, in Switzerland. But I will just give a short bio of Vadim. So he got PhD in famous Landau Institute in Moscow in 1990. And the topic was vortices in high-temperature superconductors. So, and he remains senior researcher at this institute till present time. And in 1991, Vadim moved to the ETH of Zurich, and first as a postdoc, working with Maurice Rice and Giovanni Blatter, and since then he built his research path, his research career at the ETH of Zurich, and he got habilitation from ETH of Zurich in 2003, and from March 2017, and till present time, of course, he is a professor at the Institute of Statistical Physics at the ETH of Zurich, and I can emphasize that Vadim is known for his great achievements and background research in theory of unconventional superconductors, vortices in superconductors, of course, Josephson junctions, and quantum computing. So please welcome speaker, and Vadim will present his recent work here.
Thank you very much for, does it work, microphone? I'm not. Can you hear me? Okay, then. Thank you for introduction and inviting me here. It's great pleasure to be in Bilbao. So the title of my talk, Vortices in Superconducting Magic Angle Graphene. Maybe for many of you, none of this words is clear what it means, so I will start somewhere from very far, very basic, and for experts, excuse me, we will come to what actually we are doing only towards the end of the talk. So first, superconductivity. But we start even further away. Almost 200 years ago, Michael Faraday, well, you know who Faraday was, apart from magnetism, he did many other things, and he actually managed to liquefy almost all gases which exist at the time. There were only three gases which were called permanent gases which did not want to get liquefied. And this was oxygen, hydrogen, and nitrogen. So he could not cool to that low temperature such that they would become liquid and they were called permanent. 30 years after Louis-Paul Cailletet and Raoul Pictet succeeded in producing first droplets of liquid air, so maybe if one goes with priority, since air consists of nitrogen, one can say that they liquefy nitrogen, but real quantities of oxygen and nitrogen were done another 6 years later in Poland, and they managed to go to liquid nitrogen temperature, which is 77 Kelvin. Next step was by James Dewar, who liquefied hydrogen, so which has temperature 20 kelvins, so it's quite, from 77 to 20, it's very deep down in temperature, and actually during this quest, Dewar invented what actually known to everyone nowadays, his Dewar bottle or thermos. So we use it now to store hot coffee or tea. Dewar used it to store cold nitrogen, and so on. And this was of major invention because in order to kind of liquefy, you need freeze and you need to store cold fluid, which will cool everything. And if you just put it in a bottle, it gets heated. So that's why this vacuum flask invented by Dewar was of major importance. So, but meanwhile, the new player in the game appeared, which didn't exist at the time of Faraday, and this was helium. Actually, do you know where the name helium comes from? So helium comes from the sun because it was discovered on the sun. And well, not that people flew to the sun and brought something there. They look on the sun with optical spectrometer, which was invented by Newton well, quite some time before, and then that's more or less two tubes and prism, which put spectrum and so on, and then you actually can see every element which kind of you burn produce, well, as now we understand in quantum mechanics, transition between levels in the atoms. At those times they did not know much about that, but they could associate every spectral line with element, and they look on the sun eclipse and figure out that there is a special yellow line close to sodium, but not quite, and they realized that this should be due to new elements, which was named after the sun, Helios, so that's helium. So this was in 1868, and took another 30 years till people really found it not somewhere on the sun, but on Earth, because it's difficult to liquefy gas which is in the sun, because it's very hot there. You need it on the Earth, and in 90s, they actually managed to find this helium, first from uranium, and then more like from natural gas. And so new element, one has to liquefy it. And two main competitors were, as I already mentioned, James Dewar from London, from Manchester more, Westminster, and Heike Kamerlingh-Onnes from University of Leiden. So they both work hard and try hard, but the luck was with Kamerlingh-Onnes, partially because of prosaic reasons that Kamerlingh-Onnes has more access to helium and Dewar has some shortage of supply. Well, this was something which was discovered just a few years before, so you need, in order to liquefy it, you need to have quite some amount of it, and if you have a little of it, then it's difficult to make experiments, because as you also know, if you play with balloons, helium is rather light, so if it goes out and flies away, so kind of you need enough helium to play. And Kamerlingh-Onnes was first and liquefied. Now, the interesting thing in this business, so liquefy is just some words, but you need to make cryostat, kind of to cool it. And this kind of needs, to make a fridge. Well, we call it, can you hear the difference? Okay, look, so in condensed matter, the remarkable thing is that the lower the temperature you access, the more interesting physics you find. So it's, in this sense, it's opposite to high energy physics. In high energy, kind of, you shoot elementary particle on each other, and in order to discover something, you need to shoot it with higher and higher energy to produce something. In condensed matter, it's another way around. You cool down, you see something, you cool even more down, you see something even more interesting, and so on. So that's what's called low energy physics. The lower you go, the more interesting things you find. So that's just a few examples. In Cameron Connes managed to liquefy helium and got Nobel Prize for it. Well, he discovered superconductivity, but official citation was not about superconductivity, but for liquefying helium. But kind of the remarkable discovery which he has was superconductivity. Then Kapitsa went down 2 more Kelvin and discovered superfluidity of helium. And with all these things, it's not simply to turn a knob on your refrigerator to cool it down. To go down from 4 Kelvin to 2 Kelvin to 1 Kelvin, you need to build another machine which will require another physical principle and so on and so forth. So that's a special art of in cryogenics, how to get to this and this temperature. So next was by Lee, Richardson, and Osheroff. They use Pomeranchuk cell, completely different cryogenic tool, and went to millikelvin and discovered superfluidity of helium-3. Then, another 20 years, people did evaporative cooling, went to micro or nanokelvin, and discovered Bose-Einstein condensate. So kind of the lower you go, the more interesting things you will find. Now, to go to low temperature, it's not the same as to observe superconductivity. Because if you want to liquefy something, then in principle, well, you cool and you have liquid. Or if you want to freeze water, when it gets frozen, you notice it just looking at it. Well, how much you can look through cryostat, that's another thing, but usually notice. Now, to find superconductivity, you need to measure something. Just metal which becomes superconductor, you would not see it with your eye or anything, so you need to measure resistance, for example. And Cameron Geshkenbein measured resistance. At those times, interesting, people had no idea how resistivity of normal metal, well, of metals should look like when you cool down to absolute zero. So there were all possible kind of theories. So Lord Kelvin thought that resistivity should diverge when you cool to zero temperature. Drude, from, well, textbook, drew the model of conductance in metals. So that's a person who actually created foundation of how to describe resistivity of metal. He thought that resistivity should go to zero when you cool to absolute zero. So kind of, it's surprisingly that such a basic textbook physics people did not know 120 years ago. But we also should realize that there are very many things that they didn't know. Quantum mechanics was not there. Band structure was not there, kind of what we now discuss, insulator, metals, Fermi surface, all these concepts were not there. even atom, well, of course, atom goes from Greek and so on, but Greek philosophers were kind of thinking about atom more as a philosophical concept rather than real things. So Rutherford experiment, who showed that there is nuclear and electrons around it, was done like few years before that. So kind of very basic things which we all know now were not known to people there. And well, last wish that was executed was not that long before the science, so it was in the 19th century. So everyone, so there is no surprise that this otherwise not so stupid people had strange idea about behavior of resistivity. Einstein has his own theory, which also didn't fit anywhere, and so on. Camerlin-Gonas has his own theory how resistivity should behave, and that's why he did measurements. And we see that gold, silver, and platinum, they all behave as we now know supposed behave, that resistivity was saturating at 0 temperature, but mercury was jumped and it was 0. So resistivity was 0, and this was quite a discovery. So people tried to understand it, but well, they succeeded only 50 years ago, after. So this was discovery of superconductivity, and for almost 20 years, people believe that superconductor is just a metal which has 0 resistance. So to say perfect conductor, that's just resistivity, which is 0, and so on. It is not the case, actually, and next discovery, which was major importance, was due to Walter Meissner and Robert Oxenfeld. They discover Meissner-Oxenfeld effect. Somehow, more often, it is called Meissner effect, even though they were co-authors, and but kind of maybe Oxenfeld is too long name to pronounce to anything. Kind of, it's usually called Meissner effect, but that's Meissner-Oxenfeld effect. And what they found was that if you cool the sample in magnetic field, so when it's normal metal, the magnetic field penetrates through it. And now when you cool it below transition temperature, magnetic field is expelled from superconductor. So that, which actually would not be behavior of perfect conductor. Perfect conductor makes such that magnetic field, in perfect conductor there is no electric field, and if there is no electric field, then from Maxwell equation, dB dt is rotation of electric field. If electric field is 0 for perfect conductor, then dB dt should be 0, which means that magnetic field should not change. So then if you apply field to perfect conductor, it would not penetrate there. But if you cool in the field, perfect conductor would simply keep the field inside. And that's not what superconductors does. They found that superconductor expelled field from itself, so it is, in the sense, new state of matter, which should be characterized by the fact that magnetic field is not there. And that's what actually the basics of superconducting levitation. So you have probably this type of toys and so on. Well, it's not always toys. There are levitating trains which are there, and they work on this principle that in order to expel field, you can just go out from the field, then there would be no field inside. So 2 years later, London brothers come with the first phenomenological theory of this Meissner effect. And they kind of, one can put it in a modern language in the following way. So we say that superconductivity is some kind of macroscopic phenomena where electrons form macroscopic wave function. And if it's wave function, it has modulus and it has phase. Then we write expression for current, just usual quantum mechanical expression for current, psi nabla, psi star, and so on. And this will give us, through the phase and vector potential, because phase couples with vector potential. Well, I put here 2 because of Cooper pairing. Of course, London brothers did not know about Cooper pairing and put just electron charge. But that's not that important at this moment. So you take this equation, add Maxwell equation to it, that rotational field is 4 pi over c times current. Take rotation of this equation. So when you take rotation of left-hand side, you get this term. When you take rotation of current, phase drops out because rotation of gradient is 0, and rotation of vector potential is magnetic field again, and you get this term h, and all these constants you put to some length lambda. So that's the equation, which is called London equation, which they derive. And if you solve it in one-dimensional geometry, so sample is here, vacuum is here, you apply field, then you have second derivative is proportional to the function, which means that the field decays exponentially inside material. And that's why this length, which here appears just as a combination of all this parameter, is called London penetration depth, because it describes how magnetic field penetrates inside or how it is screened by supercurrent. So that's what happens if we apply rather weak magnetic field. Now, if we apply high magnetic field, then actually this magnetic field can kill superconductivity. And there is kind of, here we have superconducting state for low field, which expelled field. But if field is higher than something, then our metal goes back to a normal metal state. It's quite interesting how this critical field was actually discovered. So it was discovered by Kamerlingh-Gonnes. And at the beginning of 20th century, Jean Perrin, well, later he will get Nobel Prize for experimental verification of Brownian motion theory of Einstein. He actually put forward an idea of making 100 kilogauss magnet or 10 Tesla magnet by making solenoid of copper, which is cool. So this was kind of challenge. And it would be like making a normal magnet like this will require huge power, because to produce 100 kilogauss, you need large current. If large current is flows, then there is Joule heat, which will heat the sample, so you need to cool it. And in order to cool, well, you need more than 1,000 liters of liquid air per hour. So the cost would be like cost of building a large ship. So this was not what you could do in the lab. And Kamerlingh-Gonnes, well, after this superconductivity was discovered in 1911, so 2 years after, Kamerlingh-Gonnes came with idea that he will make this 10 Tesla magnet by simply by making superconducting solenoid just with a size about 0.5 meter. So simple. We just need to cool the superconductor, which is doesn't cost as much as to cool this magnet, which produces heat. So that's why, for example, if you do MRI in the hospital, they put you to a cylinder, and in this cylinder there is superconducting magnet, which produce field, well, 3 times less than what they wanted to make, and it is cooled to liquid helium temperature. It's much cheaper than to make it normal. So Kammerleonov tried, and then he found very strange thing, that the same wire had critical current of 8 amperes when it was like this. When he coiled it to a cylinder, then suddenly in a cylinder critical current where superconductivity breaks down was 1 ampere. So first he thought that, well, probably when he coiled it, then there's some mechanical deformation and something wrong with the wire. So he takes another one, and again, another one, and again. And then he realized that actually it is not, superconductivity is killed not by the current that flows there, but by the magnetic field which this current produces. And if you make this solenoid, then magnetic field would be much larger by the same current, and that's why you need less current to destroy superconductivity. So that's how this phase diagram of superconductor look like for quite some time. And this actually happens for so to say type 1 superconductors. At those times they were only this type 1 superconductor, where it's either superconducting states which has no field inside, or normal metal which has field inside. So it's either or. It happens that there are other superconductors where magnetic field and superconductivity may coexist. So then the Meissner phase, which is analog for type 1, where magnetic field is out, is at low field. Normal metal is at high field, and in between there is called Shubnikov phase, where magnetic field penetrates in superconductor but doesn't destroy superconductivity. And understanding was, well, understanding or invention, in a sense, was due to Alexei Abrikosov, that magnetic field can penetrate inside superconductor in the form of thin solenoid where currents are flowing, like cylinder where currents are flowing like this, and magnetic field is flowing like this, and locally superconductivity is suppressed in a narrow region of space, and this is called Abrikosov vortex. It carries quantum of magnetic flux, pretty small amount. And so what did Abrikosov do? He started with the same London theory, the same wave function, the same current, the same Maxwell equation, but now let us assume that around this point, the phase of order parameter, when we go around, changed by 2 pi. So when we go around, we come to the same point, so wave function has to be single valued. because at this point we go around, we come to the same point, here we have the same psi. But the same psi doesn't mean the same phase. When it can go around, phase can change by integer number of 2 pi, and we still get the same wave function. So in the simplest case, it would be just 2 pi. Then if it's 2 pi, then when we take rotation of this gradient, it would not be 0. Because if we integrate rotation of gradient from the Stokes law, we transform it to area integration to contour integration, and now we integrate gradient phi over contour, which would be phi here minus phi there, and if it's changed by 2 pi, you get 2 pi. So the integral of the thing would be 0 everywhere where this point is not included in the contour, and it would be constant where we integrate it around this. Which means that this actually thing is delta function. Rotation of gradient is delta function. So then when we take this, then we get all the same term as in London theory, but from gradient we get rotation of gradient, which is delta function, and we get a source term, delta function, in the right-hand side. And this source term produce magnetic field and current, which are screening that. So that's how the vortex. So in a kind of school type of physics, one can understand vortices as real space realization of the concepts of magnetic field line. Kind of when at school I had problems, they were telling magnet, and then there is some line, magnetic field line. What is that? Well, they were showing like you put powder, and then powder something oriented, but it was always very confusing. Somehow with electric field it was not like that, but with magnetic field it was very confusing. Now you take magnet, you insert normal metal, you cool it, it becomes superconductor, and then this field gets squeezed, and you have really here tube where magnetic field is, here you have another tube, and so on. So it's really like magnetic field line, but not abstract concept which you check with compass and so on, but really field is here, but not there, neither there. So you can visualize this, see these vortices, almost with the naked eye, with different technique. So the first was observation with rather funny technique, which again, like kindergarten type of technique. You take magnetic powder, you put it on the surface of your sample, and magnetic particle, they attract to the place where gradient of magnetic field is, and then you see it. So that's called magnetic decoration. It's far from being trivial to realize technically, because these magnetic particles, you don't do like this. They are in experiment. You have a Wolfram wire, tungsten wire, like in old-fashioned light bulb. You hit it to, you push strong current, which hit it to a few thousand Kelvin Celsius doesn't, degrees, then it's hot and it's kind of emit particles, which then come to the surface of your superconductor. So in the same setup, you need this Wolfram tungsten wire, which is more than 1,000 degrees, and then this particle had to cool down, because if they come with this temperature, they will melt all your sample, but you need kind of during kind of pouring them, they're getting cold, and then they eventually heat. So there are other techniques which one can do, like was magneto-optic and so on and so forth, but these are mostly techniques which probe magnetic field of the vortex. Now this was all kind of phenomena. This phenomena were actually going parallel with studying of materials. So first, like 20, 30 years of superconductivity, people study elements. So like lead, aluminum, and so on. So this is periodic table of superconductors, well, of rather modern. And actually, as you can see, so this only white and green is not superconductor. So this brown is superconductivity at ambient pressure, and blue is superconductivity at high pressure, so which kind of shows that if you press high enough, then almost everything becomes superconductor, even iron, which is magnetic and ferromagnet, but if you press it high, then it becomes superconductor and at relatively high temperature, like 2 Kelvin. And these elements, they're usually clean, and they're usually this type 1 superconductor where magnetic field is expelled. Later in 30s, people start to look on alloys and compound, and that's kind of practical superconductors, which are like alloy of usually this niobium-3 tin or niobium-3 titanium. That's the superconductors which are used in magnets in, well, being it like in CERN, particle accelerators, or for MRI in the hospital. That's these materials, and they are dirty and type 2 superconductors, so that's why discovery of type 2 superconductor and vortices came much later, because people started to study these materials only later. Then next step was almost 40 years ago, but well, I still remember that time. Well, Eugene and me were students when this was, we were starting our PhDs where this was a discovery. And actually, till this 86, people tried to increase transition temperature and managed to something like 23 or 24 Kelvin. And they tried hard, and kind of transition temperature didn't go up, and there were many theories which tell that there is fundamental limit that you cannot have superconductivity with Tc more than 30 Kelvin. And this was a huge surprise when Alex Muller and George Bernard's discovery, actually what they discovered was a little bit higher at 36 lanthanum compound. Well, they didn't discover it by chance. So Alex Muller was studied for decades and tried to find high temperature superconductivity, and he has his own ideas where to look and so on. Well, most people believe that ideas were wrong, that he was looking for black cat in a dark room and where cat was not there, but he found it. And it was like huge rise of temperature, and like really people got crazy about superconductivity. So the like March meeting of American Physical Society was called Woodstock in physics. Well, for nowadays generation, one has to explain what Woodstock means, but this was like in 60s where all these rock bands were playing an open air concert, and then there were like people who come in and give a talk until midnight and showing that we discovered this and with that and that. So that was. And they got Nobel Prize next year after. Now for us, more important was another discovery, which was done by Andrei Geim and Konstantin Novoselov, and this is graphene. So graphene is single layer of carbon. So it's like carbon in a that's carbon atoms in a honeycomb lattice and just a single layer. So you have graphite, which you use in pencil, and if you just scratch it, then there are some graphite particles, and if you do it carefully and using Scotch tape and so on, you can find a single layer, which is called graphene, and that's what two sirs discovered. And this was kind of next explosion of, if before that, the most cited papers in physics were those who do high TC or producing samples for high TC, then after that, the most cited are those who are working in graphene. Now, another step which is important for us was that if you take so-called twistronic, if you take one layer of graphene, you put another layer of graphene, and you rotate them on some angle, then you get this kind of picture, which is called moire pattern, just from close from that moire. And it has superstructure with a super cell, which has a size depending on the angle. So this, if you calculate band structure, and actually was first calculated numerically by Alan MacDonald and Bystritzer, who proposed that if you twist on a special, so to say, magic angle about 1 degree, then you will have so-called flat bands, so where spectrum is very flat and effective mass is very large, and you may have very interesting phenomena there, including superconductivity. So this was 2000, well, I think 2013 was theory paper, and 2018, people at MIT actually realized this. And what is good in this twist material, that you can change property, what kind of unusual, in other materials is kind of doping. Well, in semiconductors, you know, like p-n junction, when you dope, you get, well, our modern electronics is based on doping, and usually you do it chemically. Here, you apply voltage to your sample, and voltage change occupation, change number of carriers, and as a result of it, you change all properties. So this is phase diagram where you have and you do it all in the same sample. So you don't take different materials, preparing and so on. You just change voltage on the device, and you go change carrier density, and you go from superconductor to mot insulator to another superconductor to metal, and so on and so forth. And this brought kind of this physics of atomically thin van der Waals superconductor. Van der Waals is a name because these layers, which are twisted, they are coupled together by weak van der Waals forces. Well, two hydrogen atoms are attracted by van der Waals forces, so that's this kind of why it's called van der Waals superconductor. Now the question, how does abricose vortex look like in this very thin superconductor? And this was studied, well, not century, half a century before this by Mr. Pearl, who look on how vortex looks like in thin film of thickness d. And then he figured out that, well, if you have thin film, then the current that flows there will produce very little magnetic field, just because current density can be large, but total current is small, so magnetic field is small, so it's very difficult to screen magnetic field. That's why the effective screening length is called Pearl length. It's not London lambda, but lambda multiplied by another lambda over d factor, so it's much larger. And this Pearl vortex looks like, at the distance much larger than this Pearl length, it looks like magnetic monopole. So in the upper space, it's monopole with field going up. In outside, in the lower, it is like magnetic monopole with fields going inside. And the total flux quanta is actually realized in the area of the order of this Pearl length. So this Pearl length for atomically thin would be very large, so this vortex would be actually pretty challenging to observe with all this magnetic probe, because magnetic field which it produces is so tiny. Now the question, how can we still see this vortex and detect them in one or another way? And then idea is that if we cannot measure field, then maybe we can measure phase, because field is not screened, which means that the phase, the current which is flowing everywhere, and so it produces phase far outside of vortex. Now, how do we measure phase in superconductor? And here we come to Josephson effect, which was due to Brian Josephson. So the simple picture of it, you take two superconductors with order parameter psi1 here, psi2 here, and you couple them, and you look how the energy depends, what is the energy of the junction between two superconductors. So they should talk to each other. In the spirit of Landau theory, you should couple one order parameter to another. Now, psi is complex function, but energy is real. So you should make the simplest combination would be psi1 times psi2 star plus psi1 star times psi2. That would be real real quantity which you made from two complex number. And if you put psi through the phase, then it would depend on the phase difference as cosine of it. And taking derivative of it, you obtain that the current is some critical current times sinus of phase difference. So if you have two different phases, then critical current, well, current from the junction is sinus of the phase difference between them. If you put it in magnetic field, then magnetic field modifies phase difference in this way, that phase changes linearly when you go along the junction. And current is sinus of phase difference, so current density would oscillate. Here current would flow from right to left, here from left to right, and so on. Total current is integral of this, and we obtain that critical current is, when we integrate, is sinus of flux through the junction divided by flux. It's called Fraunhofer pattern, so that because, not because Fraunhofer discovered it in Josephson junction, but because it is given by the same formula that Fraunhofer diffraction, which you study in optics. So if you take single slit and look on the electric field on the screen away from slit, then you have amplitude of electric field is sinus of angle divided by angle. That's Fraunhofer diffraction. Now here we have the same functional dependence, but for completely different thing. So this is for bulk superconductor where magnetic field is expelled from inside, and then the flux which comes there, so this flux, which is in this formula, is the flux in the junction. Now, for atomically thin superconductor, we cannot use this formula because field is not expelled. Field is everywhere. Currents are flowing everywhere, so we should do better job. And, well, we can do it. And then instead of sinus flux over flux, there would be Bessel function. And this actually has quite different shape. So this is orange is this formula, which is for planar junction. And this red, well, the different, oh, can one see it? Well, here you can see, here you cannot, that they try to play what is lambda here, what is the flux, but one can see that you cannot really fit because the second maxima is much lower than this here. So now I come to our work. Finally, so this experiment was done at ETH in the group of Klaus Enslin, and the key figure is Marta Perega, very good PhD student of Klaus. So she designed experiment, made the sample, did measurements, and so on. So what did she do? She did magic angle twisted 4-layered graphene. Before I was telling that you take 2 layers and twist. Now you take 4 layers and twist in the opposite direction by another angle, 1.75 degrees. Well, there are, first people discover bilayered graphene, then 3 layers, then 4 layers, so kind of people are working hard there. Then, so this is this graphene, 4-layered graphene. It's put encapsulated in boron nitride substrate, and you apply gates, bottom gates, top gates, and finger gates with which you produce junction. So that's geometry. Its length like 6 micron. Here it's about 1 micron. And here by gates, so by applied voltage, you make junction. So you put gate such that in the leads, the resistance is 0, so you tune it to superconducting states. And in the junction, you tune density of carrier in the high resistive states, and that's how you make, how she made the junction. And that's this Fraunhofer pattern which they found. They claim that that's the best Josephson junction made from this graphene. Like people use graphene as a weak link between 2 ordinary superconductors. So this was done before. Here, kind of the breakthrough, as they tell, was to make full junction where end leads and the junction itself are all made from the same material graphene. Then you don't have this problem with contacts and so on and so forth. So she did, and that's the best Fraunhofer pattern which exists there. Now, if you look more carefully, then you see that there's some irregular structure. Here there is something, here there is something, here there is something, and so on. So it is not as perfect as one could think. And if we go closer, then we see that critical current go and then jump. Go up, jump. Go up. So there are all these jumps. This when we increase field from negative to positive, and then we go from positive to negative, then it goes and then jump to 0. Goes, jump, and so on. So there are different jumps, so that arrows are kind of quite visible jumps. So they try to look more carefully on them. So how do you get this curve? So that's what is plotted is differential resistance. So they measure IV curve, and now when they go with current, it goes linear, linear, linear. Then during these measurements, it's jump to 0 voltage, then jump back, and so on. So you have kind of IV which is jumping when you change current. if you do it multiple times, so this like 100 different IV curves, then they see that they jump everywhere for any current. You have all these jumps. What you also can do, you can fix the current at this point and wait and measure voltage. And then you see that voltage as a function of time now jump from high value to zero, so that's on the scale of 10 minutes, that zoom, so it stays at high volt, then jump, up, jump, and so on. So that's again the same with zoom. Then they can put histogram, put counts, what is lifetime of normal state and superconducting state, so how many counts, so this is like 8 minutes, so this so many, you run experiment many times and look how often it can stay in this state for this amount of time, and in this state for this. And it's all fit pretty well to exponential behavior, which is typical property of decay physics. So if you have, let's say, nuclear decay, you take 1,000 atoms with a lifetime, whatever it is, it doesn't mean that after this time, 500 will decay, because some will decay immediately, some will decay in 1,000 years. Just probability, well, the number of these decays goes exponentially down, so it looks like both high voltage state and superconducting states decay to each other. So how we can try to understand it, and what we came to idea that actually these jumps are produced by vortices in the leads that come in to the leads. So if you have vortex in the leads, then because screening is poor, the current here modify Josephson phase and modify critical current of Josephson junction. So what we should do, we should, to this phase shift produced by magnetic field, we should add phase shift produced by vortex, well, which is given by this relatively complicated formula. And that's, for example, if you can place vortex in a special position such that at zero field it would be not maximum of current, but zero of critical current. So then what we did was put in vortices in all possible positions and look how Fraunhofer pattern would look like. So this is how it behaves when we move vortex from symmetry axis from infinity to here, then there's this displacement. If we move it from the axis to this, it is this type of thing. So what do we have? Without vortex, let's assume we have this Fraunhofer pattern. And with vortex, we have such Fraunhofer pattern. It's important to realize that this pattern with vortex shifts always to the right. This is because the current which is produced by vortex is in the opposite direction than the Meissner current. Because Meissner current screens the field from outside, and vortex current screens the field from the vortex from inside. So they have to flow in the opposite direction. Then this Meissner's current reduces the current produced by the field, which is equivalent to shifting this Fraunhofer pattern to the right. And, well, this is kind of, that's experiment, that's theoretical plot when we place vortices kind of here, this and this in this position, which looks pretty similar to what they observe. Of course, we don't know whether what they measure is vortices or not. That's our interpretation. But that fits rather well. What else can we know? Assume we put a current here, and we wait. And vortices, by thermal or quantum fluctuation, jump in and out. Then critical current switches between this and that. And our current in one state is below critical, which means that there should be no voltage, or above critical, that there is voltage. So then the voltage would oscillate together with vortices coming in and out. And from knowing how they go, we can derive the barrier. And from this barrier, we can find superfluid stiffness. So that's what we then analyze the data. This is the switching. The time of switch exponentially depends on temperature. So that fits to exponential behavior. From here, we can extract the barrier. Or here, it's kind of time goes up exponentially, not time rate goes up. Then one can calculate the potential for vortex as a function of coordinate for different fields. And there is barrier which vortex should come for going in, and this will be barrier for going out. So this barrier can be extracted simply by this fitting what the time of event, and from this we can get that this is about 2 Kelvin. From the other side, from this theory, this barrier is about energy of vortex in the film, which is flux quantum divided by London length square. So equating this to this, we get London penetration depth about 3 microns and superfluid density about 1 Kelvin, which agrees well with the recent kinetic inductance study of 2 leading groups from Harvard and MIT. They do another bilayer and 3-layer material, but they got very similar value of superfluid density, which actually means that temperature of Berezinski-Kosteles-Tauris transition would be about 1 Kelvin. So, and that's the temperature close to TC, so this physics of is of major importance here. So, well, that's the summary of what we did, that actually because of vortices can switch current in Josephson junction made in graphene, and one can use Josephson effect there to learn about properties of vortices in graphene, and in particular also one can extract superfluid density and other things which otherwise is rather difficult to get. Thank you for your attention.
Yeah, thanks a lot. Yeah, regarding actually the that figure where the upper one, you're having the understood correctly as a function of.
Should I scroll?
No, that one. It's
Yeah.
that one actually.
Yeah.
You actually have resistivity as a function of the applied magnetic field. It's magnetic field and intensity.
Well, that's current on the axis, okay. That's magnetic field,
okay.
And color is resistivity, differential resistivity. So blue is low resistivity, and well, dark blue is low resistivity, white is high resistivity, and high resistivity is because IV curve looks like this, and then steep rise, and then so when it's kind of steep rise, then you have high differential resistivity, and then it's less. Yeah.
Yeah, and you had an image which was like a VI relation for a particular value of applied magnetic field. I think in the paper was about well, I can't remember 1.8 or something. And then you had that kind of VI curve, which was kind of jumping between normal and superconductive and normal phases. It's all the jumps between the normal and the superconducting phases, actually.
I just go to this.
Yeah, that one, yeah. Yeah, that's what actually, if it works out, yeah.
Yep, yes.
Okay, so, but that's actually, you have actually computed time evolutions, and then that's what you are graphing there. So it's actually time dependent, if I understood correctly, which is why you have the time dependence on the right.
Well, I think what is in this blue is more or less this
Yeah, it's
thing.
superconducting, yeah.
And this, when you do it kind of many times and you plot, that's why it's kind of this blue-white color. There is some noise in colors because sometimes you find this, sometimes you find that. Okay. So,
and obviously that's the hysteresis or whatever you want to call it is depending on the applied B field.
Yes. So this curve depends on applied field. Then also which of these states has longer lifetime also depends on applied field and current and so on. So there is a rather complicated analysis. So actually, our work was not done in that way. They observed these jumps and didn't understand what it is and came to us, and we tried to understand what are these jumps due to, and that's how it all.
The other thing, you actually mentioned the Kosterlitz-Tauler, but is your device big enough that you can think of a macroscopic description looking into Kosterlitz-Tauler is sensible? Because you're actually saying that the vortices have to be very, very big. So I haven't got a clue as to the actual scale, sorry.
Well,
that's why.
They did not, they in this experiment did not study Berezinski-Kosterlitz-Tauler transition. And if you have this vortex and vortex pairs and so on, then in finite region you also would have this type of behavior. It would be crossover and so on. They did not study that kind of what happens at close to transition temperature and so on and so forth. In I mentioned these two works from Harvard, MIT, where they measure kinetic inductance. Kinetic inductance probes superfluid density directly, and if there is a BKT transition, then there should be jump of superfluid density, so-called Nelson-Kosterlitz jump, from some fixed value to 0. Nobody saw that. But if you have finite size effect and so on, then it can be masked and so on. So this, in the sense, this way, for this magic angle graphene, nobody knew what is superfluid density and what is London penetration depth, because that's new compound and it has all these flat bands which are very narrow bands which would be high, very large effective mass, and if you have completely flat band, then superfluid density should be 0, and so on and so forth, and nobody knew what it is. So the lambda which we extracted, like 2-3 microns, is about 10 times bigger than for typical superconductors, where it is about 1,000-2,000 angstroms. So here is like 20 times more, which means superfluid density is like a few hundred times less. So it's really low superfluid density. But what to expect at what it is, nobody knew. And depending on it, if superfluid density would be 5 times more, then kind of Kosterlitz-Tauler would be far away. So just it seems that numbers are such that we are close to where to expect BKT physics. And we did not know where it should be because for this material, nobody knew what is superfluid density. Because kind of the problem is that they're so thin that you cannot really measure their magnetic response. So you cannot measure screening because it's not screened. So then, well, there was quite a big achievement of these two groups where they do like use kinetic inductance and got something. But before that, you could fantasize and put any number for this penetration depth. We were rather happy that the numbers that we get from completely different analysis are rather similar to what these two groups obtain.
Yeah, so it's a very naive question. I'm just saying that you were trying to explain these jumps by appearance of a vortex, but the vortex has a topological charge, has a winding number. So shouldn't you have a vortex, anti-vortex produced at the same time?
No.
How can you produce one topological number?
No, there's no problem in that. I mean, you may have vortex coming in and out. It doesn't, you have finite system. So in infinite system, vortex, if you take like, if you have infinite film, then you cannot make a single vortex because it has another topological charge and so on. So then in infinite film, vortices, like thermally induced vortices, can be created by dissociation of vortex-anti-vortex pair, and that's what is Berezinski-Kosteles-Saulis transition. If you have finite film, then you can have vortex just jumping from outside. It's not any problem. And actually, that's a big, these vortices in thin films, that's a big problem for qubits, where they have in the leads and so on some vortices which they don't know whether they're coming from, and they kind of have their own life and produce decoherence. So kind of another system like vortices are known to exist and actually to harm that. So if you have finite system where energy of vortex is finite, then this large logarithm for infinite, which makes them impossible in thermodynamic limits, in the finite size, so this barrier from which we calculate, it actually has logarithm of the size divided by coherence length. But for this system, this logarithm is about unity.
Yeah, I wasn't so concerned about the energy. I was more concerned about the topological number.
In the finite system, that's not a problem to create, well, you...
Something in the boundary.
Yes, yes.
This, you know, your system is just a set of carbon atoms. But why isn't it possible then to seemingly it's impossible to accurately explain the data?
You mean from first principles?
Well, yes, because I mean, you 990
Yes and no. So, as I mentioned, that this magic angle twist was first predicted theoretically by calculating band structure and so on, that there's this special angle 1.1 degree. And a few years after, people really produce this twist which was predicted and discover what was predicted. So in this sense, you are right. But not everything one can predict. There are two things there. Even for usual material, like superconducting property, transition temperature, like to predict which material should be superconducting and which not, is very hard, and it's much better after we know transition temperature to fit our theory which predicts that. But if you don't know, then to predict, like even for simplest lithium, which is as close to hydrogen, so the simplest, like for many years it was not superconducting, now it is superconducting, so it's very hard to predict. Because in general, because transition temperature exponentially depends on strength of electron interaction and you have large exponent, large thing in the exponent which you don't really know, and there is like Coulomb repulsion which makes, and then phonon attraction and so on, and that's kind of what makes to predict which, not even transition temperature, but which material would be superconducting and which not, is almost impossible. Well, it's possible a posteriori after we know. Graphene is, from one side, simple because, well, the band structure of graphene with these Dirac cones were calculated, well, not century, but almost in 40s. And it has weak interaction and so on, so this Dirac electrons can be calculated. But then when it comes here, you have prediction was then from band structure that there would be flat bands, which means that the spectrum would be very flat, which means that there would be very narrow bands. And when you have narrow bands, then electron interaction becomes of major importance. And then to predict what you have not free electrons, but strongly interacting electrons, and to predict life of strongly interacting electrons is much more difficult. That's why kind of, for example, they got, from this measurement, they got this small superfluid density, but they were arguing that it's actually not that small because there is some quantum geometry which will give something and so on. So there are all possible predictions, but you have strongly interacting electrons because of this flat band, and for strongly interacting system, it's very difficult to predict anything. There was one question behind.